In 8085, the serial input output operations are performed by two pins. One is known as the serial output data or SOD, other is the serial input data or SID. So, these two are for serial input and output, and this as far as the operation is concerned, the operation is controlled by these instructions RIM and SIM, read interrupt mask and set interrupt mask. So, as we have seen previously that this RIM and SIM instructions, so they have got one bit configured in the accumulator that will be acting as the serial input and output. So, this is how it takes place. First of all, we will discuss about the SIM instruction and the serial output part. So, this is the this shows that how this can be done. Okay. So, this diagram if you remember, so we have got this accumulator setting where this bit 0 to bit 4. So, they are for this interrupt masking and this R 7.5 bit, 5 is not used, and this bit number 6 is for disabling and enabling serial output data. So, SDE, serial data enable, you can say. So, if it is 0, then this serial output data, this is disabled, and if it is 1, then this is enabled, and this SD or this SDO bit. So, this is for the serial output data. So, that will hold the data that should be sent to the outside through this pin. So, if you want to transmit some bit serially, so you can put the bit in this bit number 7 of the accumulator and enable this SDE bit and then execute the SIM instruction. So, that the bit that is stored here will be sent through this line. Next, you put another bit here and setting that SDE to in the enable mode. So, again the next bit will go through this serially. So, this is how this SIM can be used for serial transmission of data. Similarly, you can for serial input part. So, we can take help of the RIM instruction. So, RIM accumulator configuration is like this. So, rest of the bits we have discussed while talking about while talking about the interrupts, and this bit number 7 is the SDI, serial data input. So, this particular bit can be used. So, when you are using this RIM instruction, this rest of the bits, that is bit number 0 to 6, they are set according to the interrupt mask settings and all that, but this SDI bit. So, this is coming from the SID pin of the 8085 processor, and this bit will be having the value of the SID pin. So, whatever is coming serially on the SID pin, so that will be put into this particular bit. So, we can use this RIM and SIM instructions for doing this serial data input and output operation. What about port selection? So, since this SID and SOD, so they are single bit pin, and we do not have to have different devices, a number of devices connected to it and all that. So, that concept is not there. So, we do not need to bother about the setting up of input and output ports. So, SID is for input and SOD is for output. So, they may be connected to the same device, and it is the device's responsibility to figure out whether it is an input operation or output operation. So, that way so these two pins SID and SOD, so they are by themselves they are the ports, okay, for serial ports. Now, this SID, this SI and SIM and RIM instructions, so they are similar to this out and in instructions. So, we will see this out and in instructions later. So, this out and in instructions, they are for parallel output. Okay. So, you will see that. So, for parallel output, for 8 bit output, so you can use out instruction, for 8 bit input we can use in instruction. So, only difference is that in case of out it is 8 bit, and in case of SIM it is 1 bit, in case of in it is again 8 bit input, in case of RIM it is single bit input. So, that way this SOD and SID pins are used as ports. So, this is an example that talks about how this serial communication can take place. Okay. So, let us take an example of transmitting one ASCII character stored in the register B using this SOD line. Okay. So, we have to first so how many bits to be transmitted altogether? So, 1 start bit, 2 stop bits and 8 bits of data. So, total 11 bits are to be transmitted. Okay. So, we keep a counter in the C register for the 11 bits. So, MVI C, 0V hex. So, that will set the C register to the decimal value 11. Then the next instruction XRA A. So, this is XOR accumulator with accumulator register. So, if you XOR A the accumulator with itself, so the content will become 0. So, the accumulator content will become 0 and carry flag will also be cleared. Then we have to move this, we move the pattern 80 to this A register, that will set that D7 bit to 1. So, D7 bit, so and then we rotate right. So, bring the carry into D7 and that bit, this bit shifts and D6 becomes 1. Then we execute the sim instruction. So, this actually outputs the start bit. So, if I just go back and see that sim. So, for putting the start bit, so this bit should be 0 because start bit is 0 and this line should be 1. So, this is done by the first few instructions that we have discussed. So, here this setting this doing this RAR, rotate accumulator right. So, this will be bringing the carry flag from the carry bit from the carry flag into the D7 bit and the D7 bit will get shifted to D6 bit. So, the D7 bit will act as that start bit and D6 bit will be the setting of that SDE, the serial data enable, and then the sim instruction. So, this D7 bit 0 will go to the output. So, that will be the start bit. Then we have to wait for some bit time. So, we have some delay routine for the bit time. So, which is not shown here explicitly. So, you can write a small delay routine by finding out what is the bit time for the type of crystal that is connected to 8085 processor, its frequency, and then you can find out what should be the timing, and you have to have this baud rate setting between the device and the processor and all that. So, based on that you can find out what is the bit time. So, you can put a delay routine which is equivalent to this bit time delay. Then we set carry to 1 and then move A comma B. So, this will place the character in that we had in the B register into A register. Then we do a RAR. So, that way this D0 that we have, the first character that is there in the accumulator. So, that the D0 bit. So, that will go to carry and the carry was set to 1 as you see here. So, that carry will become that carry will now get shifted to D7. This intermediary result we save in the B register, okay, because after that the content will be changed when we execute this sim and all that. So, this is set to the value is set into the B register. So, at the end of it we have got the bit that we want to transmit, the next bit that we want to transmit is available in the carry, okay, and the D7 bit is 1 by this set carry, and then when we do this RAR. So, this carry bit comes to the D7 and then this the bit that we want to transmit comes to the carry after this RAR instruction. Then we save this intermediary value and then we decrement C. So, in decrement C, so 1 bit has been transmitted, the start bit has been transmitted. So, it is decremented by 1 and jump on not 0. So, we come to the next bit. So, in the next bit you see that again the D7 bit will be set to 1 and it will be rotated right. So, the D7 will go to the D6 bit enabling the SDE and this sim instruction will transmit the. So, carry bit will be coming to the D7 bit, okay, and carry bit is actually holding the least significant bit that we have in the character to be transmitted now. So, that will be coming to this through this sim. So, that will be outputted to the serial output data. So, this way we can execute this program and by this individual characters will be transmitted one after the other. And of course, what is not shown here is the finally, we need to transmit 2 stop bits. So, that is not shown here explicitly. So, after transmitting this 8 bits, so we have to transmit the carry bits. So, that part of the program is not shown here. So, you can add that to the bottom of the program. Next, we will look into some more examples of this 8085 programming. So, we have seen many statements. So, we will use those statements to write some sample programs. So, you can just practice them you can write some similar such programs to get confidence about the programming features of 8085. The first program that we consider is to count number of ones in the content of D register and store the count in the B register. So, how do we do this thing? So, in the B register we store 00, that is the initial count of number of ones that we have in the B register, in the D register. So, that count is initialized to 0, and MVI C, 08 hex. So, this C register is holding like how many times I need to check. Okay. The policy that we will follow is basically we will check the carry bit. Okay. So, policy that we follow is if this is the content, if this is the content of this B register, then what we will do, if this is the content of the D register, then what we do, we transfer this content to the A register first, and then in the A register we do some rotation through carry. Okay. So, through this carry bit we rotate it, okay. And if the carry bit is set, if the carry bit becomes set by this fashion, sorry, it is not from here, it actually goes from this point. Okay. So, the same the bit, the most significant bit, it goes to the carry as well as the least significant position. Now, if when this bit is rotated, so if the carry becomes set, that means the bit was 1, and if the carry is not set, then the bit is 0. So, we do 8 such rotations, and in whichever, if the in the rotation, if the bit becomes 0, then we do not increase the B register, but if the bit is 1, the carry bit is 1, we increment the register, so that we can get the value there. Okay. We can get, we can count that 1. So, this is done here in the program. You see that this rotate right, okay, rotate accumulator right, and then jump on no carry to skip. So, in that case, if the carry is not set, then we do not count it as the bit that we have as a 1. Okay. So, B register is not incremented. So, then we decrement the C value, because we have done one rotation, and jump on not 0 to back. So, we will go back to this point, again rotate the accumulator, and we will do this thing. So, this way, after this the loop completes, so in the C register, in the B register, we will have the number of ones that we have in the originally in the D register. Okay. So, that will be available in the B register now. So, if we look into another program, so we want to sort 10 numbers given stored in memory location 2200 onwards, and we want to sort them in ascending order. So, for sorting we use the simple bubble sort type of algorithm. So, we just compare two successive numbers, and if they are out of order, we change the order of those two numbers, and if they are in proper order, then we do not alter them, and this process is repeated for the all possible pairs of numbers. Okay. So, this is the algorithm that we follow. So, we initialize this B register to the value 9, because the first index it can go from 1 to 9. So, and the second index will be going from 1 2 to 10. So, that way we do it. So, LXI H2200 hex. So, that will be stored, that is the initialized memory pointer. So, it will be initialized, and then we move this C, 09 hex. So, this will initialize the counter 2. Okay. The other counter is also initialized. Move A, M. So, we will get the first number into the accumulator. Then the INX H, it will increment the memory pointer. So, we have come to the next number. So, we have got the numbers stored in this fashion. So, if this is the array where we have got the numbers stored. So, the first number is available in the A register now, then the HL pair is incremented, and we compare. So, compare M. So, this HL pair is pointing to this address now. So, we compare the content of this location with the content of the accumulator register. So, if the content of the accumulator is less than content of this memory location, or they are same. Suppose this value is say x and this value is say y. So, the possibilities are x is less than y, or x is less or equal y, other possibility is x is greater than y. So, if x is less or equal y, we do not need to do anything, they are already in the proper order. If x is greater than y, in that case we need to change the order. So, on jump on carry and jump on 0, so these two cases, so we do not do anything. So, we do not if they are less, do not interchange, if they are equal, then also do not interchange, otherwise we have to interchange them. So, what do we do? So, move d comma m. So, this instruction, so this will move the content of this memory location onto the D register. So, the D register now has the value D register has got the value y, okay. D register has got the value y, and then it says move m comma a. So, this location it was containing y previously, now this value becomes equal to x, move m comma a, this will make it equal to x. Next, now we need to store the value of y onto the previous memory location. So, for that purpose we decrement h. So, HL pair now HL pair now goes back to the HL pair now goes back to the point that we have here. So, HL pair goes there one position back by DCX and then move m comma d. So, now D register is having the value y. So, that will be moved here. So, this location gets the value y. So, as a result this x and y values have got interchanged, and then we again take that HL pair back to this position. So, this INX H. So, this will take the HL pair back to the next position. We decrement C. So, this one iteration of the inner loop is over, jump on not 0 to back, it will take us to back, and if it is the back is here. So, we get the next number. So, that way we can will go back to that position, and if it is otherwise, so if it is 0, we have completed one iteration, one complete iteration of this counter 2. We decrement this B register, and then if it is B register is not 0. So, we go back, start the next iteration of the outer loop. Okay. We start the next iteration of the outer loop starting with this LXIB. So, this process is repeated for 9 times. Okay. So, as a result the entire array will get sorted. Okay. So, this way we do this algorithm of sorting 10 numbers in the ascending order. Next, we will look into another program, that calculates the sum of a series of even numbers from the list of numbers. So, in the list we have got both even numbers and odd numbers, and the numbers are stored from the location 2200, and how many numbers are there in the set. So, that is stored in the location 2200, that is the length of the list, and the list actually starts at location 2201. So, at that location 2200 we have got the number of numbers. So, this is the memory. So, at 2200 we have got the number of numbers. So, if I have got only say 4 entries, then this value will be 4, and here I have got the actual numbers. These individual numbers may be even or odd. So, the program is to sum up these even numbers, and there is an assumption that the sum can be that the total output sum is 8-bit wide only. So, there will be no overflow after we have added all the even numbers. So, we can ignore the carries and store the sum at memory location 2210. Finally, the sum has to be stored at location 2210. So, how do we do this program? So, we first load accumulator 2200 hex. So, that will have the number of numbers in the A register. then move C comma A. So, it will move the count value to the C register, then MVI B00 hex. So, the sum, so the B is holding the intermediary sum. So, that is initialized to 0. LXI H2201 hex. So, this will initialize the pointer to the first location of the array, and then move A comma M. So, this will get the first number that we have, and it will get it into the A register. Then ANI 01 hex. So, we need to check whether the number is even or odd. Okay. So, for that purpose, how to do it? So, we need to check if the number is even, then this the least significant bit, that is the bit D0 will be 0 if the number is even. On the other hand, if the number is odd, then this bit will be 1. So, this is exactly what is checked here. So, we see whether we do a masking of that number with 01 hex. So, only the least significant bit is 1, and as a result, if the result becomes 0 of this due to this ending, if the result becomes 0, that means the number is an even number. So, in that case, sorry, if the number is not 0, then it is an odd number. So, in that case, we do not need to add it. But if the number is after this ending, if the value becomes 0, that means the number is even. So, we need to add it. So, we first move this B register content to A register, because B was holding the intermediary sum. So, that is moved into the A register, then add M. So, add M will add the content of the memory location pointed to by this HL pair with the A register, and the value is in the A register, and then the value is again moved to the B register. So, the intermediary result is stored back onto the B register. Then this H register is incremented, this C value C register is decremented. So, because we have already processed one number. So, the C register is decremented, and as long as this C register content is not 0, we will go back to this jump on not 0 back. So, it will come back here. Now, it will access the next memory location and add it. So, once this C register value becomes 0, that means we have added all the even numbers. So, the value has to be stored at location 2210 hex. So, that is done here. So, the store accumulator 2210 hex. So, this will be storing the number at location 2210 hex. Okay. Sorry. Next, we look into another program that will unpack the packed BCD numbers. So, packed BCD numbers are like this, like when we are storing, say when we are storing say number, say a number say 42. Okay. So, 42 in decimal. So, 42 in decimal. So, if you want to store it, so if you when you are storing in the computer, so this 42 will be converted into bit pattern, like so this is so this is 1 2 3 4 5 6 7 8. So, this is the 42 representation that we have in the binary number system. So, if you are storing the number in a computer system, then what will happen? So, this will be stored as an 8-bit pattern. Okay. So, there is another number system which is known as BCD, which stands for binary coded decimal. This stands for binary coded decimal. So, here what is done is that this individual digits of this decimal number system, they are coded into binary. So, we have got these two digits here 4 and 2. So, they will be coded individually, and they will be stored in the into 4 bits of a byte. Okay. So, what will happen is that this number will be stored as first the digit is 4. So, this will be stored as 0 1 0 0, and the next digit is 2. So, this is 0 0 1 0. So, this is how the number will be stored. So, first 4 bit and the next 4 bit. So, that is the BCD coding of the number 42. Now, if the number is stored like this, and then suppose the number is stored at memory location 3000. So, at memory location 3000 we have got the number 0100, 0010. So, this is the 4-bit pattern, 8-bit pattern that we have. Now, what the program will do, so it will break this number into 2 8-bit numbers, okay, and store the results at 3001 and 3002. At 3001, so it will be storing the first digit, that is it will be storing this 0100, and the next location it will store the number 2, that is the next digit 2. So, that is 0010, and rest of the bits are 0. Okay. So, this when I say it is 0010, so this most significant bits are all 0. So, the actual number that is stored is 0000 0100. Similarly, at the next location the actual number that is stored is 0000 0010. So, this is the thing that we want. So, I have got at location 3000 the number like this. So, I want to convert it into 2 digits separately and store them in an unpacked form. So, this is called packed BCD form, the 3000 location, that is called packed BCD form, because we are packing 2 digits of BCD number into 1 byte. Okay. So, each digit takes 4 bits. So, I can put 2 such digits in a location, that is why it is called packed number. So, you can unpack it. So, how to do this? So, first we get the number into the accumulator. So, this LDA 3000 hex, so it will get the packed BCD number from memory into the accumulator. Then we store the number in the B register. So, move A comma B comma A. So, this will save this value of A register into B register. Then this C is made equal to 4, and then we AND immediate with F0. So, if we AND immediate with F0, that means this is F0 hex. So, what happens is that from this number I want to get only this part. So, this part will be this part I want to convert to 0. So, if I AND with F0, that is ANDing with say 1 1 1 1 0 0 0 0. So, the result is 0 1 0 0 0 0 0 0 after this ANDing. So, and then we do a rotate right through carry. So, this will be rotated 4 times, and we decrement C. So, this rotation, so C is initialized to 4. So, this loop will be repeated 4 times. So, ZNZ L1. So, this will be repeating 4 times. As a result, rotate right. So, if we rotate right, then this part, this result part, so they will be coming to the, they will be rotated and coming to this side. So, after this rotation, the result will be 0 0 0 0 0 1 0 0. Okay. So, that is what we want to store now. So, the accumulator content is like this. So, that value will be stored at location 3001. Now, we do so the one part is done. Now, the next digit that we have. So, we move the content of register B into register A, and again, and now we AND immediate with 0f hex. So, if we AND immediate, so with this content with the content 0100 0010. So, if we AND with 0f hex 00001111. So, we will get this part will become all 0. So, this will become 0010. So, you will get back this part here, and the other things will be 0. So, now here we do not need to rotate anything, because this is the pattern that I want to store. So, this will be stored in the location 3002. So, this will be the value will be stored in the location 2 location 2. Okay. So, that will be stored there. So, then this halt instruction, this is for terminating the program. So, halt instruction will stop the processor, as we know. So, in your case, so you may have some other loops etcetera here to make the program leave, or you make some cases we transfer the control to the monitor program of the kit, of the microprocessor kit on which we are working, so that we can check the content of different registers and see whether the program has been done correctly or not.